there, it's Shannon Matchick-Myers, and today we'll be looking at section 14.2 from the Larson and Edwards calculus text. And this covers double integrals and volume. So basically, our goals for today, we want to be able to use a double integral to represent the volume of a solid region, use properties of double integrals, and evaluate a double integral as an iterated integral. All right, so let's warm it on up here. We've got this iterated integral that's going from 0 to pi, and then 0 to pi on our x, right? Because dx is on the outside, and 0 to pi over 2 on our y. And then f of x and y, so kind of keep this in mind. Z equals f of x and y, which is equal to sine squared at x times cosine squared at y, all right? So let's check it out. So the integral from 0 to pi, I'm going to go ahead, since we're integrating with respect to y first, I'll go ahead and factor out the sine squared at x from the innermost integral, and then we'll be going from 0 to pi over 2 for our cosine squared at y dy, and then this whole thing, right, will be integrated with respect to x. So here we go. This will be equal to the integral from 0 to pi. And then we have our sine squared at x still hanging out. And recall the power reducing formula. I can actually also factor out a 2, or a 1/2 rather. And then I'll have the integral from 0 to pi over 2 of quantity. This was cosine squared at y, so it would be 1 plus cosine at 2y with respect to y. And then this whole thing, of course, I will have to integrate with respect to x. So for those of you that forgot, recall that sine squared at some a is equal to 1/2 times, oh, that's not the one I did, but we'll be using it soon enough, is equal to 1/2 times 1 minus cosine at 2a, and cosine squared at some angle a is 1/2 times 1 plus cosine at 2a. So that second one is the one, the trig identity that I used for this inner integral. All right, so that will be equivalent to, let's see, that 1/2 can come out from everything because it's a constant. We'll have the integral from 0 to pi of sine squared at x. And then performing the integration here, we will have y plus, now remember, we need to have a 2 times 2 dy, so I need to divide by 2 as well in order to complete the integration. And that will give us y plus 1/2 sine 2y. That's going to go from y equals 0 to y equals pi over 2. And then all of this we will have to integrate with respect to x. Groovy? Okay, so now, here we go. We will have 1/2 integral 0 to pi sine squared at x. And then let's see, our lower limit, do you see, will zero out completely because sine at 0 is 0. So our upper limit is going to be pi over 2 plus sine at 2 times pi over 2 is sine at pi, which will zero out. So I will have just pi over 2. All right, and then dx, factoring out the pi over 2, I'll have pi over 4 times 1/2. I'm going to do that identity. So we'll be going from 0 to pi. And when I do that identity, I'll have 1 minus cosine at 2x with respect to x. This will give us pi over 8 times x. Again, we're going to have to adjust. We need a 2 dx to do our integrations just for this part, so I'll divide by 2. So we'll end up having x and then minus sine (2x over 2). And then we'll have that it being evaluated from x is 0, 2x is pi, and again, this will be pi over 8 times pi minus sine at 2 pi is 0, okay? And then lower limit of integration, we'd have 0 minus 0. So this will just be pi. And then at the end of the day, we'll get pi squared over 8. How'd you do? Awesome. Awesome, awesome, awesome. Like what we just did on our warm-up problem was z equal to f at x and y. So this stuff right here, that's basically giving you the height, okay, the height of infinitely many right rectangular prisms, if you will, that you could make. So instead of infinitely many summing infinitely many rectangular regions like you do for finding area, you're really finding infinitely many right rectangular prisms. So what changes, though, this is the area, right? So here, you know, if you think about what's happening is your y is going from 0 to pi, or sorry, your x is going from 0 to pi, and your y is going from 0 to pi over 2. And so that's really just some rectangular region, right? And then your height values are represented by sine squared at x times cosine squared at y. So here's the visual of what, you know, what we found. And if you think about it, you're making infinitely many of these. Let's see, I don't know if it'll show up well or not, but infinitely many so do you see, like down here you'd have, you know, something like this, and so that would be kind of one of your right rectangular prisms, etc. And you know, you'd have the more of these little, prisms that you use, the better approximation you would get, for your volume. All right. So this is really what we found. I'm just going to leave that one because otherwise I think I'll pretty much ruin the idea. So it's kind of like this. And then maybe if I erase that one, something like this. Right. So anyway, you'd have infinitely many of these rectangular prisms. And what's changing, instead of only a dx or a dy, it's really, dx, dy, you take a look at, how the area is changing. And that gives you, your incremental change. Okay. So let's go ahead and just take a look at this one. This is just kind of a reminder of, how you can use, the more rectangular prisms that you use, the better your approximation is going to be. And you can take it from anywhere you want in the interval. So basically it's saying, okay, let's use, we've got this over some square region R. We've got some function f over a square region R. So the values that are in the body of the table are the height of your right rectangular prisms. So if we divide into 16 equal parts, and we first start by picking the, say, left endpoint and bottom, the left bottom endpoint with which to do our area calculations, right? You'd have these values for your z. Does that make sense? And so you would have your integral. This would represent your integral from 0 to 4, for both our dy and dx's. And what that would be, it would be approximately, well, if you're going dy first, right? dy first, you would be going 32, right? So you would be looking at these values right here, right? And you'd be summing them up, all right? And summing them up because of the way we set up our integral. It's both vertically and horizontally simple. And so it's fine. So 32 plus 31 plus 28 plus 23, that's that first column. And then plus 31 plus 30 plus 27 plus 22. And then plus 28 plus 27 plus 24 plus 19. And then our last would be plus 23 plus 22 plus 19 plus 14. And that ends up giving a result of, if I computed it correctly, I believe that gives us 400. Okay. Now, if I go, so that was like using left lower endpoint, right? So for our area. So now if I move from that, and if I go to using the rightmost on the left and the uppermost on the y for my area to pick my squares I make, I'll be having this purple stuff right here. So I'd be, again, since I'm setting it up dy dx, I'll be looking at these. And so the integral from 0 to 4 is still 0 to 4 because you can pick any number within the ith interval. So, and we'd have our f of xy dy dx, and that's going to be approximately, so now what do we have? 30 plus 27 plus 22 plus 15 plus, and then again, you know, continuing 27 plus 24 plus 19 plus 12. And if that was approximate, so, and then if I added this correctly, I would get 272. So you could average these to try to get a better picture of what the volume is, right? And you know, see what we would get. And if you know, so that an average for the volume, you just add the 2 and divide by 2. But basically, what you have going on here is I just wanted to really emphasize the fact that you're looking at this dA, this change in area. Okay. All right. So now let's get into our definitions. So double integral. If f is defined on a closed bounded region R in the xy plane, then the double integral of f over R is given by. So R is this region here. We've got our f of x and y, dA, and that's going to be really kind of approximately equal to the limit as the norm of delta approaches 0. So basically, as the widest subinterval of our area approaches 0 of f of xi, yi, and delta ai. Okay, so provided the limit exists. So as that happens, you know, of course, you're going to get infinitely many more of these subintervals. All right. So if this limit exists, then f is integrable over R. So the volume of a solid region, if f is integrable over a plane region R, and f of xy is greater than or equal to 0 for all x, y, and r, then the volume of the solid region that lies above R and below the graph of f is defined as our volume equals the double integral over the region R of f of x and y dA. Cool so far? All right, so now let's see what we've got going on. So let's sketch the region R and evaluate the iterated integral here. So we've got the integral from 0 to 4 and then 1/2 y to root y of x squared y squared times y squared dx dy. So let's look at kind of a picture of what's going on with our area region. All right, so y is going from 0 to 4, right, and x is going from 1/2 y to root y. So if we take a look, at the planar region, okay, then let's see, you know, what's going to happen. So here, now we know y is going from 0 to 4. Now let's just kind of set up what we have going on. We've got dx dy going here, and so remember, if the inside is going to be functions of y, and so when we have 0 less than or equal to y less than or equal to 4, let's see what our boundaries would be. Y is 0 and y is 4. But the other one we have is 1/2 y is less than or equal to x is less than or equal to the square root of y, right? And so our boundaries are x equals 1/2 y, but we're used to seeing it more as what? If I isolated y, I would get 2x for the purposes of graphing. And x is equal to root y, and that would give us y is equal to x squared. Cool so far? All right, but remember that y is bounded between 0 and 4, and so you're going to have an ordered pair at 0, 0, right? And then when y is 4, x would be 2. And then when y is 1, x would be 1, and that is that second bound. That's this one. And then the other one is going to be so this one right here, y is 2x. So again, you've got a point at 0, 0. You've got a point at 2, 4. And these would just connect. Cool so far? Now, here, that represents the area, okay? Our little rectangle is going to be a dy. And of course, you know, this here is our region R. Okay. Okay, so here we go. Let's check it out. So this is setting up this is the picture of the integral as it is shown here. So we would end up having, you know, this would be equivalent to the integral from 0 to 4. I'm going to take out the y squared, and then we're going to do the integral from 1/2 y to root y of x squared, and then dx, and then this whole thing here we'll have to do with respect to y. So that'll give us the integral from 0 to 4, y squared times 1/2, I'm factoring, or sorry, 1/3, because it'll be x cubed over 3, 1/3 x cubed, and then x is going from 1/2 y to root y. And then we're going to have to do this whole thing. We're going to have to integrate with respect to y. Cool so far? Okay, so now we'll have the integral from 0 to 4. And we'll have, I'll just write it as y squared over 3. And then this is going to give us y, the square root of y is the same as y to the 1/2. So when I cube that, I will get y to the 3/2 minus 1/8 cubing the 1/2 y cubed. Cool so far? All right. So then now I'm going to have to integrate all that with respect to y. So let's go ahead and clean this up a bit. So we will get the integral from 0 to 4, bringing in the, so we'll have what? Y to the 7/2. So 1/3 y to the 7/2 minus 1/24 y to the 5th. And we're going to integrate this with respect to y. So this will give us the integral from 0 to 4. And then, no, we're evaluating it, my bad. So this is going to give us, increasing by 1, we would have what, 9/2. So 1/3 times 2/9 y to the 9/2 minus 1/24 times 1/6 y to the 6. That's going to be evaluated from y is 0 to y is 4. Cleaning that up a little bit, we'll have 2/27 y to the 9/2 minus 1/144 y to the 6. And then those will be evaluated from y is 0 to y is 4. So we will get, let's see, the square root of 4 is 2, and then we'd have 2 to the 9th. So 2/27 times 2 to the 9th is 512 minus 1/144, and y to the 6 is 4096. And then do you see the lower limit of integration is just going to zero out for each of them? So putting that all together, we'll end up with, if I did my math right, we will end up with 256 over 27 cubic units. Cool, cool? Okay, so that's the region. Now, how would we go about, just for fun, we weren't asked to do this, but how would we go about setting this up as dy dx? You want to practice that? So we would have the same graph, right? But in this graph, remember, we had functions of y, right? In this first one. So that one was x was equal to root y, and then the purple graph was x is equal to 1/2 y. And so if we kind of changed it around, looked at that real quick. So we'd still have, you know, the same picture, right? So we'd have something at 0, 0 and at 2, 4. And this one would be but what would happen is our region, right? So we still have, you know, this region, but our rectangles would be vertical, right? So this one would now be y is x squared, the pink, and we would have the purple as y is 2x. And so our integral would look like, so the most outside thing, if we're doing dy dx, is going to be what x ranges on, and x is going from 0 to 2. Do you see that? And then we would have y is going from, the topmost graph is 2x, and the bottommost graph is x squared. And then we would still have the f of x and y, x squared, y squared. And then this would be dy dx. Make sense? Okay. So all right, so, and then you'll get, of course, the same result if you integrate. Now, let's take a look at properties of double integrals. So it turns out just these properties are very similar to what you've learned before. It turns out that if you have a constant times your function of x and y, it can be taken in or out of the iterated integral. If you have a sum or difference of functions of x and y, you can split the integrals, the iterated integrals. If you have, if your integral is always, it's always going to be greater than or equal to 0 as long as f of x and y is greater than or equal to 0. Okay, so that's important for volume. And number 4, if the iterated integral of f of x and y with respect to a is greater than or equal to the iterated integral of g of x and y dA, that's going to always be true if, so that statement will be true if your f of x and y is always greater than or equal to your g of x and y. And then finally, you can split an iterated integral as long as r, whoops, that's my blue, where r is the union of two non-overlapping subregions, R1 and R2. Okay, so these are all very similar to things that we had done for, in prior properties for integrals where it's just one integral. All right, let f be, this is Fubini's theorem, let f be continuous on a plane region R if R is defined by a less than or equal to x less than or equal to b and g1 at x less than or equal to y less than or equal to g2 at x, where g1 and g2 are continuous on the closed interval from a to b. Then it turns out that the double integral over some region of f of x and y dA is equal to the integral from a to b, and then the integral of g1 at x to g2 at x of, dy dx. If r is defined by c less than or equal to y less than or equal to d, and h1 at y is less than or equal to x is less than or equal to h2 at y, where h1 and h2 are continuous on the closed interval from c to d, then what do you think will happen? We'll have the double integral over some region of f of x and y dA would then be the integral from c to d, right? And the integral from h1 of y to h2 of y, and this time it would be dx dy. Groovy? Okay, so now let's take a look at this problem here. Set up an integrated integral. Sorry. Iterated integral for both orders of integration, and use the more convenient order to evaluate over the region R. All right, so let's check this out. So our region R is this triangle bounded by 4 minus x, y is 0, and x is 0. So let's take a look at it and check this out. So if we did this, we'll do a general drawing first to figure out what order might be, which one might be better. Okay, so let's see, our picture would look like that. And then, so that represents the sky. And then, y is 0 and x is 0 are just going to be, so that's our x is 0. Our y is 0 is this bound here. Cool, cool. And then this is our region. All right, so I'm going to go ahead and copy this. And that way we can figure out how we want to set it up. So here we go. If we were doing this vertically simple, let's see what it'll look like. Vertically simple means that we would have dx, right? Like that. And then topmost minus bottommost. I mean, that's going to be a pretty simple one, I'm thinking. So let's just, name what we have. This one, we would have y equals 4 minus x. And y is 0. And so our integral would be set up as zero to 4 on the dx, and then 0 to 4 minus x on the dy. Oops, sorry. Remember, this is just setting up our region. And so we'd still have our f of x and y. So x e to the y, and that would be dy dx. Cool so far? All right. So the way this one would look is you would have, and you would isolate x, right? So x would be 4 minus y, right? Is that line. And then remember, it would have to be rightmost minus leftmost, okay? And so you would be looking at the purple one, x equals 0, and this is the horizontally simple one. And so our integral would then be the integral from, again, it'll be 0 to 4. And then we'd be going from 0 to 4 minus y along our x. So then we'd have x e to the y dx dy. Cool, cool? Okay, so now you kind of want to think about integration, right? Because we need to integrate this stuff. And so I'm wondering which one will be easier to integrate. So sometimes, you might want to just dive in and try it. But let's see, if I was integrating the first one, the top one, we'd be integrating with respect to y first. So we would just get e to the y. And then we'd be putting in a 4 minus x. And that's something in the exponent of the y. That's something we can certainly integrate by using integration by parts, I think, right? Yeah. All right, so now the other one, if we integrate with respect to x first, we get like an x squared over 2. And then we'd have quantity 4 minus y squared over 2. And that's going to be harder to integrate. So I'm saying that this guy, harder to integrate. But you might not know, and so you might just have to try it out and see what happens. Okay, so we're gonna pick the top one. So we're gonna say we're gonna do the integral from 0 to 4, integral from 0 to 4 minus x, and that's of x e to the y dy dx. So this will be equal to the integral from 0 to 4, and then keeping the x constant, we would get x e to the y, right? Because the integral of e to the y with respect to y is just e to the y, right? And that's going to be evaluated from y is 0 to y is 4 minus x, and we still have our dx hanging out. Cool, cool? I'll just go ahead and do this. All right, so that's going to be the integral from 0 to 4 of x times the upper limit of integration will be e to the 4 minus x. And then minus lower limit of integration, we'd have e to the 0. And This will give us integral from 0 to 4 of x e to the 4 minus x with respect to x. And then, you know what, I'm going to just do another integral minus the integral from 0 to 4 of 1 dx from my e to, or no, it'll be x, sorry. It'll be x times 1, which will be x dx. Cool, cool? Okay, so I'm going to say C above. Nah, we can do it down here. So for our integration by parts setup, we would have u is equal to x, and so du is equal to dx. dv would equal to e to the 4 minus x, and so then v would be negative e to the 4 minus x. Cool, cool? Okay, so coming up here, that first integral will be u times v, so negative x e to the 4 minus x, and then minus the integral of v du, negative e to the 4 minus x dx. We're still integrating from 0 to 4. All of that will be from 0 to 4. And then minus x squared over 2 from x is 0 to x is 4. So now we'll have negative x e to the 4 minus x minus e to the 4 minus x. That's evaluated from x is 0 to x is 4. And then minus, let's see, x squared for the second one would be 16 over 2, and then the second term would 0 out. So we'd have minus 8. Cool so far? All right, so now we will have, I'm going to do another line and simplify. If we factor out a negative e to the 4 minus x, we'll be left with x plus 1. And that's going to be evaluated from x is 0 to x is 4. We've got this minus 8 hanging out. So we will get negative e to the 0, because 4 minus 4 is 0, times 5. And then minus a minus is plus. And then when I plug in 0, I'd get e to the 4th times 1. And I still have minus 8 hanging out. So this is going to give me negative 5 minus 8 is negative 13. So I'd have e to the 4th minus 13. And that's our result. Cool, cool? Okay, so next up, we have set up a double integral to find the volume of the solid bounded by the graphs of the equations. X squared plus c squared is 1, y squared plus z squared is 1, and this is in the first octant. The first octant. So in the first octant, x, y, and z are all positive, right? They're all greater than or equal to 0. So basically, let's just kind of check out what we have. I mean, we need to figure out, well, what what is our f of x and y, right? So here, if we look at these two equations, do you see that z squared would equal to 1 minus x squared? And so z would be plus or minus the square root of that, but we're in the first octant, so we're going to just take the positive root. And similarly, z squared is equal to 1 minus y squared. And so z, being in the first octant, is going to be the square root of 1 minus y squared. Groovy? So, okay, equating these things, right? And also remembering that x and y are positive, we would have root 1 minus x squared would have to equal to root 1 minus y squared. So 1 minus x squared has to equal to 1 minus y squared. And that means x squared has to equal y squared. And so x has to be y. And that, of course, is since x and y are greater than or equal to 0. Groovy? Okay. So, we can set it up however we want. Let's take a look. If we have depending on how we want to set it up, I think I'm just going to set it up by doing it vertically simple. Okay. So if I do that, I've got x and I've got y. And I've got a b in the first octant, so they're all positive. And z is also positive. And if you take a look at the square root, the square root, if I'm doing dy dx, right, at the end, then I need to know what x is moving on, right? So do you see that x and y will both be bound between 0 and 1 inclusive in order for that square root, their square roots to be true, and the fact that they are supposed to be positive. So here we go. Point at 0, 0 and 1, 1 for the graph of y equals x. Okay. And then there's going to be a bound here at y equals 0. And then remember x would be going from x is 0 to x is 1. And so our region is here. And we're setting it up as vertically simple. So this will be dx. Cool? So that's our setup. So now let's check out our integral, right? So we would have the integral from, or our volume would be the integral from 0 to 1 and 0 to x. Okay, since z is equal to both root 1 minus x squared and root 1 minus y squared, we pick which one to use. So since we're setting this up as vertically simple, right, what we're going to do is we're going to go ahead and use the root 1 minus x squared, okay? And you'll see why in a minute. So dy dx. So then our volume will equal to the integral from 0 to 1, and then we're going to get root 1 minus x squared times y, right? Because we're treating the x as constant. And y will go from 0 to x. And hopefully you can see we'll be set up for our next integral. So that's going to be just the integral from 0 to 1, x times root 1 minus x with respect to x. Sorry, 1 minus x squared with respect to x. And then we need to have a negative 2, right, in order to integrate. And so if I multiply on the outside by negative 1/2, I balance. So the volume will be equal to negative 1/2 times 1 minus x squared raised to the 3/2. And x is going from 0 to 1. And then, of course, we have to divide that by 3/2 as well. So the volume will be negative 1/3 times 1 minus 1 squared to the 3/2 is 0. And 1 minus 0 squared to the 3/2 is 1. And so our volume will be 1/3 of a cubic unit. Cool, cool? Awesome. All right, so here's an application for us. Find the average value of f of x and y over the region R, where average value is 1 over a times the double integral over R of f of x and y dA, where a is the area of R. And we're given that f of x and y is x times y. So all we have here is just a rectangle for our area base here. And we've been given these vertices. So it looks like x is going from 0 to 4 and y is going from 0 to 2. So our x is 0 to x is 4. And then our y is going to be y is 0, or y is 2 and y is 0. Cool, cool. And so this is our region. Okay, so here we go. The area, we know here, it's 4 times 2, which is 8, right? Base times height. And so with our average value in general being equal to 1 over a times the double integral. So if I make this vertically simple, right, I'm doing the dy dx, and so y is ranging from 0 to 2, x is ranging from 0 to 4. And so this will end up being equal to 1 over 8, integral 0 to 4, integral 0 to 2, xy dy dx. And so that'll be 1/8 integral 0 to 4. Let's see, I would end up getting x times y squared over 2, y being evaluated from 0 to 2. So let's see, I think that'll just be 2 squared is 4, 4 over 2 is 2, minus 0. So I'd end up with 2/8, bringing that out, integral from 0 to 4 of x dx. Sorry, I forgot to leave my dx here. And so that'll be 1/4 times x squared over 2, and x is ranging from 0 to 4. So 1/8 times 4 squared is 16 minus 0 squared. So we would end up getting 2. So the average value is 2. Groovy? All right, so that's it for today. I hope you had a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, hey, please subscribe and tell your friends. Bye.